So now let's go to today's presentation. Today we're going to talk about workflows with programmable source and programmable filter in ParaView. And let me switch to the first slide. So just a couple of words on ParaView. I assume that most of you are familiar with ParaView. If not, then ParaView is a general purpose three-dimensional visualization tool. So it's an open source tool that is multi-platform. So you can download the source and compile for Linux, Windows, and Mac. And it's also available as a precompiled binary. So the latest version is, the latest stable version is 5.8, but you can also now download the 5.9 release candidate 4, which I'm going to use today for demos. And this tool is your general purpose visualization data analysis tool. So that means that you can use it in many different fields for two-dimensional and especially for three-dimensional data. So it was built for analysis of very large data sets on essentially supercomputing, on supercomputers, excuse me. So on distributed memory machines, but you can also run it on your own laptop if your data set can fit into memory. And it supports interactive visualization. So you work with the menu and the GUI elements, but you can also script your entire visualization with Python. So it supports client server for remote interactive visualization. You can run it in batch mode without opening any graphical windows on a remote cluster, et cetera, et cetera. For parallelism, it uses MPI, message processing interface. So that's industry standard for distributed memory programming. And ParaView is based on VTK, which stands for Visualization Toolkit. So VTK was written by the same folks who wrote ParaView. So there is tight integration between VTK. So VTK is the visualization and computer graphics library that's been around for almost 30 years now. So since 1992, I think, the first official release. And it's a library that was written originally in C++. Now it's available in other languages, including Python and JavaScript. And ParaView is essentially a GUI on top of VTK. So everything you can do in ParaView, sorry, everything you can do in VTK, you can do in ParaView. And by the way, I have not mentioned today's slides are available. There is a link at the bottom of the slide. So you can see, you can go to bit.ly/these pages in your web browser. And it opens this page we have for visualization resources. And the very first link here, if you scroll a little bit down, you will see today's talk. So there are slides that I'm showing on my screen, and then there is a zip file with various scripts that we're going to be running today. Well, I'm going to be running on my screen today. So we use ParaView as a default teaching tool for three-dimensional scientific visualization. And typically we teach a full day workshop on ParaView. So we start with basic introduction to ParaView for beginners, when we cover we'll cover using filters and constructing a basic workflow. We then will go to animation, scripting, and then we end that full day workshop with remote visualization. But there are a lot of topics that I simply do not have time to cover in a full day workshop. And the way I approach this is I try to give at least a couple of webinars every semester. So these are the topics that are more advanced, that do not fit into the basic full day workshop. And so today we're going to be talking about the programmable filter and source in ParaView. So the topics that are marked here in green I already covered in various webinars and other presentations. So some of these are available as recordings and slides on the visualization page that you see at the bottom. A couple of talks from, actually a couple of topics from NVIDIA. So using NVIDIA Optics Ray Tracing Library and working with NVIDIA Index framework on supercomputers, on large distributed memory systems, these two topics are going to be covered in an invited webinar we scheduled for April 28th. And somebody from NVIDIA is going to talk on these topics. So let's jump to a programmable filter and programmable source. Why do you need a programmable filter in ParaView? Well, the simple answer is if you want to create and modify VTK objects. So let me give you a very simple example. Let's say we have a three-dimensional data set. And, we have a three-dimensional data set defined on a Cartesian mesh. So let's say some function on a three-dimensional Cartesian mesh. And we want to plot a projection of this function onto one of the planes, let's say an XY plane, right? So we want to compute the projection, and we want to plot this projection off at some distance from the cube, right? So this projection is a new discretization, so it's not the original three-dimensional discretization, it's a two-dimensional plane that is offset relative to the original data set. And there are things like a calculator in ParaView and also Python calculator. So what a calculator lets you do is you can compute a new variable based on existing variables. But that new variable will be defined on the same discretization as your original discretization, right? So any new variable you define with calculator or Python calculator will be defined on the same three-dimensional mesh. So a calculator or Python calculator will not let you create a new plane with the two-dimensional projection array. So for that, you have to use a programmable filter. Working with programmable filters is actually quite well documented, but it's a fairly advanced topic, so I think it's good to show a lot of demos today. And the idea is really very simple. So you apply a programmable filter to any object in the pipeline browser in ParaView, and then you set the output data set type. So it could be as either same as input. So basically you feed some input into this programmable filter, and the output is going to be the same as input. Or you can select one of the provided predefined VTK data types. There are about 10 or so types that are available. And then once you select the output type, you fill in the script box with your code, your Python code. So basically you take your input, and you can have multiple inputs. So depending on how many input streams you have feeding data into the programmable filter, you will have input 0, maybe inputs 1, maybe inputs 2, and so on. So usually there is a single input, so it's called input 0. And then you use the points in this input, so let's say X, Y, and Z coordinates, as well as some data arrays defined on top of the input data points. And then you compute the output. So by default, when you select the output type same as input, then your input is simply copied into your output, and then you can modify your output and then visualize it right later on. So in some cases, depending on the type of the output, you might need to fill in some code into the second box that is called request information script box. And I'm going to show you several examples of this. And then you hit apply, and you create a new VTK object that you can visualize inside your visualization window in ParaView. All right, so a programmable source is very simple, very similar, nearly identical to programmable filter, with only one difference is that it does not have an input. So a programmable source basically is self-contained. It does not process any external data in the pipeline browser. So you can do two things with the programmable source. You can build an object programmatically. So you can have, let's say, three-dimensional function that you define right inside the Python script inside your programmable source, or you can use programmable source Python scripting there to write your own reader for your own custom data from a file. So let's say if you have a file in some format that ParaView cannot understand, then you can actually write your own Python reader, and let's say using NumPy or some other, pandas or some other functions, external libraries, and then you can convert it into a VTK data structure, and then this object will be in memory in ParaView, and now you can actually visualize it. All right, so let's start with a very simple example. I already have ParaView running. So what I'm going to do is I'll show this slide. So we're going to start with we're going to initialize a two-dimensional function, a two-dimensional Gaussian, centered at 0, 0, and then we're going to warp it into the third dimension. So we're going to start a plane source. A plane source is necessary because we want to create a discretization. So we need an input to our programmable filter. So we're going to initialize an input plane mesh, two-dimensional mesh at 100 squared resolution. Then at each mesh point, we're going to calculate a Gaussian function that is given by this expression. So essentially, it's inputs to the Python calculator, which is the output from the plane will go into the Python calculator. So there's a single input 0, and it has points x. So here are the points x coordinates of your mesh points, and here are the y coordinates of your mesh points. So we define this Gaussian with this value of sigma, centered at 0, 0, and then we apply a programmable filter to it. So we choose the output data set type same as input, and then we print some information, and then modify the output in the script. So let's do that. Here we have, oops, actually I should probably drag, yeah, I should drag this zoom window. Just give me a second because it, to a different screen. Okay, great. All right, so I'm going to start with a programmable, sorry, I'm going to start with sources plane. So the way to initialize this in ParaView, you can go to sources and you can either hit search or alphabetical. So you will see a plane here. What I'm going to do today is I actually have, I have a shortcut on my keyboard. So for me, it's Command L, but you can actually program it by preferences. So every time I press Command L on my computer, it will start a search box and I can easily search for sources or filters. So it's the same shortcut for both sources and filters, Command L. So I'm going to do Command L, and then I will search for plane source, hit Enter. And then here I want to increase the resolution. So I'm going to do 100 by 100 mesh points. I'm going to hit Apply. So here it generated a plane and I switched to two-dimensional view. So now when I try to drag it, it does not spin because it's a two-dimensional view, right? And you can actually visualize it as a mesh. So you see there are 100 by 100 mesh points. So let me make it 3D, three-dimensional view. And here's my two-dimensional mesh in 3D. And then to this mesh, I'm going to apply a Python calculator. So I'm going to click on the plane in the part-time browser. I'm going to search for a Python calculator. And then in here, I'm going to paste the text from the slides. So the rename result is going to be P. And then the expression is going to be this mathematical value, the Gaussian. So X, this is X, this is Y. And then I'm going to hit Apply. And it generated my Gaussian. So if you take a look at the output, you see that there's a function P, array P, that ranges from this value to this value. It's a float single precision array. And then we can actually color the plane by the value of the array function P, right? So it's a two-dimensional Gaussian. So now I'm going to use the programmable, programmable filter to actually warp it into the third dimension. So I'll apply programmable filter to the output of the Python calculator, set output type same as input, and then I'll do some printing before modifying the output. So click on the Python calculator, and then I search for programmable filter. So here it is. And then here I go to properties, output data set type, same as input. And that what I'm going to do is I will actually paste this line into the code. So before modifying the output, I just want to print some information. So here I'm going to the output and I'm printing the shape of the points array. You will see, let's hit apply. Oh, yeah, great. Output messages. And you see that it's actually a two-dimensional array where the number of points is 10,201. So that's 101 squared. So we have 100 squared cells and 101 squared mesh points. So this number of mesh points, and then 3 is the X, Y, and Z components, so coordinates for each point. The point here is that the output is, even though the function is two-dimensional, our plane is two-dimensional, but the output is three-dimensional. And the reason for that is because the input is three-dimensional as well. So if you actually print the points, simply print output points, it will print the points and you will see that the third coordinate, Z coordinate is 0 everywhere. So now we're going to modify it. We're going to modify this third coordinate, so warp into the third dimension. So the first line I'm going to paste is this one. I'm actually comment out the print line, and then I'm going to paste this line. So here we are simply offsetting, setting the Z coordinate of each point in the output to the value of my Gaussian. Oh, sorry, actually, no, that's not what I want to do. Sorry, this is a different script. I want to do this, sorry. So what we offset it we set it to the value of the point data array in my input. So input is coming from the Python calculator, right? So in the Python calculator, there's the array called P, and then I'm using the value of that array at each point to offset my function into the third dimension, to offset each point in the output into the third dimension. And then I'm going to compute the data array, which is based on these point data P array that I defined in the calculator. And then I'm going to append this data array to my output. So output point data append, and in the output is going to be called pin-u. So in the input, it was called p. In the output is going to be called pin-u. And then I hit apply. So here you see that now I have a three-dimensional object. And you see that the object is, yeah, so here we have this pin-u array that ranges from this value to this value. And we can actually color our surface by the pin-u array. So our surface is defined on a mesh that is simply offset from the second dimension into the third dimension, right? So if you have any questions, feel free to ask questions. Unmute yourself or type questions into the chat. And I see that Mary has been asking questions as well. So in this slide, I just want to mention that it's actually possible to access your arrays and data points in several different ways in VDK. So there are several syntaxes that you can use. And for example, point data, you can simply print it as an array, or you can access it through the function. And the same for the point. So for example, you can print the XYZ coordinates of, let's say, point number 1005 using this syntax or this syntax. So both are valid in VDK. Some of you who have been paying attention to what I was doing might actually see that I don't need the Python calculator in my pipeline because I can do everything by simply setting the offset to the value of my Gaussian. And you would be right. So let me show you this solution. I'll go to ParaView, and then I'm going to delete the programmable filter. I'm going to delete the Python calculator, and I will start with this two-dimensional mesh, right? So there's no function defined yet. We just have a 100 by 100 two-dimensional mesh. And then to this mesh, click on the mesh. I'm going to apply the programmable filter. So, and then same as input for the output. And then I'm going to paste these three lines. So I'm simply setting the Z offset for each point in the output to the value of my Gaussian function. So I don't have to do it inside Python calculator. I can do it directly in the programmable filter. And then I compute the data array. And then I simply append this data array as a variable called pin-u to my output. And the result is going to be exactly the same. So in the output, I have the pin-u variable. And then I can color my data set by this new variable. So here's a very simple pipeline where I set up a source, a plain two-dimensional mesh, and I need this mesh because in the programmable filter, I have to have an input. So programmable filter needs to have an input. So it takes the input. In this case, it copies it into the output. So output is exactly the same as input. And then I modify this output right here in the script. Okay, so let's switch to programmable source. Programmable source, as I mentioned, does not take any input. It just acts, well, it's just self-contained. So I'm going to start from scratch. Let's just erase everything from ParaView. And I will call the programmable source. So now you see that when I search for programmable, the source is actually highlighted and the filter is not, because I don't have any objects to which I can apply the filter. So, but I can apply the source. And in the programmable source, let me print the following. So I'm going to say print type and then output. And then for the output, I'm going to select actually the default VDK polygonal data. So let me hit apply. And I have the output messages open. So you see it prints the type of the output. It's polygonal data. So VDK polygonal data makes sense. Let me switch to something else. Let's say unstructured VDK unstructured grid. And then I'm going to run it. And it prints that now my type of output is VDK unstructured grid. So let me show you one more. We're gonna see examples with all these these three output types later on today. So I'm gonna select. I selected image data. So VDK image data is just a Cartesian mesh, right? So it's a three-dimensional Cartesian mesh, and now you see that my output is it's called data set, but it's actually underneath. It's essentially a three-dimensional Cartesian mesh. All right. Oh, by the way, and if you are interested in what kind of data structures are inside output, so everything in the namespace of the output, then the standard Python way to print this is simply printing the dir function, and that will simply tell you these are the things you can access inside output. So there is, for example, cell data, there is point data, somewhere there's point data, then there are points, et cetera, et cetera. So you can actually print and modify these variables. All right, so the first example we're going to do with the programmable source is we'll write a CSV reader. So in ParaView, you can actually read a CSV file directly. You don't have to use programmable source for this, but just for instructional purposes, we are going to write a simple programmable source where we read data from a file. So this file is simply a CSV file. And actually, let me drag my, oops. Let's see my, yeah. Let me show you what it looks like. So let me make it bigger. So here is just a CSV file where we have 4 columns. So the columns are called X, Y, Z, and scalar. And this will be the X, Y, Z coordinates of the points. And then the 4th column is the value of the scalar function. All right, so what we're doing here is we're simply importing NumPy as NP. And then in NP, there is a really useful utility gen from TXT. So basically it reads the text file and it recognizes different types of delimiters. So our delimiter is a comma, and then it converts everything into 3 arrays. And then we're going to go through the names of actually 4 arrays. There are 4 columns, 4 arrays. We're going through these 4 arrays, and then we are defining a NumPy array to which we feed the data from the respective column. And then we simply append the data, that NumPy array, to the output of our programmable filter, which we set to VDK table. So the goal of this particular example is to read a CSV file and then store its output in a VDK table object. Okay, so let me just show the, on the other screen, I'm looking at my text that I'm going to paste into ParaView. So here I'm going to start from scratch, and then I'm going to apply a programmable source. The output I'm going to say set to VDK table, and then into the script I'm going to paste these lines that I just went through. So I'm going to say apply, and here we go. So it read the table. Now the table is actually in memory. And if you go to information property, you see there are 4 columns. So there's X, Y, Z, and there's a scalar column. So this is exactly what would happen if you just read this CSV file directly into ParaView using the CSV reader. But in our case, we did that by the programmable source. And if you want to visualize it, well, ParaView doesn't know what to do with this data. It just sees a CSV file. So it sees 4 columns. And to visualize it, you need to pass it through a filter that is called table to. So depending on whether you have isolated points or a structured grid, in my case, I have 1,000 points that are meant to be on a 10 by 10 by 10 Cartesian mesh. So I'm passing it through table to structured grid. And then I'm in the properties here, I need to specify that X goes from 1 to 10, Y goes from 1 to 10, then Z goes from 1 to 10, and then the X column supplies the X coordinate, Y supplies Y coordinate, and the same for Z. And then I hit apply. And now I have my object defined. So now if I go to the click on information, I see the output from this table to structured grid filter. And I see the output is actually a structured grid that is size 10 by 10 by 10. And on top of this grid, I have this scalar array that is a double precision and covers this data range. So in order to see this array, all I need to do is simply, well, make it visible and then switch to the surface view. And then here is my data array, right? So it's a 3-dimensional function that is defined, that was read from this CSV file. All right, any questions at this point? All right, so you might say, well, why do we need to go through these two objects? So first we have a programmable source, and then we take the data, tabular data, and convert it to a Cartesian mesh. Can't we do everything in one step? And the answer is yes, of course. You can do that very easily everything inside the programmable filter. So in this case, you will have to change the output type. So switch from VTK table to VTK image data. So in VTK, that is a Cartesian mesh. And then you read data using the same NP function from the same file. And then here I'm simply processing the sizes of the length of the columns to find the number of points in X, Y, and Z, but actually all of them are equal to 10. And then I set up, my output is a VTK image data object. So I need to tell ParaView to tell VTK about the properties of this object. So number of dimensions, origin, so that's one of the XYZ coordinates of one of the corners, spacing between the adjacent planes in XYZ, extent, so that is also similar to, so basically similar to the number of points in each dimension, but it just tells that the index in the X dimension runs from 0 to an X minus 1 and so on. And then on top of these three-dimensional Cartesian mesh, I have a single array. So once means a single array of type VTK float, so single precision, that will be assigned to it. Then I take my NumPy array, which is a data scalar column, and then I simply convert it to a VTK array, and then I say that there's one component, so there's just a single variable. Well, it's one variable, and one component means it's a scalar field, not a vector field. I set the name density, and then I simply take that VTK array, and then I set it as I append it to the points, right? So the output point data. So on top of each point, I define these three-dimensional array. So let's just take this this code and run it inside the programmable filter. So I'll go to ParaView, and then I will start from scratch. So I'm going to actually, oops, sorry. I'm going to click this button. And then I will apply the programmable source, sorry, starting from scratch. And then for the output type, I'm going to say VTK image data, so three-dimensional Cartesian mesh. And then I'm going to paste the code that I just showed in the slide. So here we're reading the data and then processing the data and then setting the values to each point on our Cartesian mesh. So I hit apply and it works. So it did not complain. There are no error messages. And if you click on the information panel, you see that our three-dimensional Cartesian mesh, so image means a Cartesian mesh in ParaView, was created. So there's a density field that ranges from this value to this value, and its size, so this mesh is 10 by 10 by 10, but nothing is actually plotted, right? So if I switch to a surface view, try to arrange, focus on my view, and nothing printed. And the reason for this is, and this applies only to VTK image data as far as I know, is that you actually need to supply the metadata. So you have to describe this Cartesian mesh to ParaView. Not sure why you need to do it twice, not just in the script, but in the second box, script request information, but this is the way it was programmed in ParaView. So basically what I need to do is, in the second box, you need to tell ParaView that you're dealing with a mesh of size 10 by 10 by 10. So I'm gonna paste these 3 lines into the second box that says script request information. So, and then I hit apply. And now my mesh, as you can see, my data set appears, right? So I can actually call it by the value of density. And here's my function. So here we did everything in a single step, the programmable source. We read the data into NumPy array, then we converted the NumPy array into a VTK array, and then we added the VTK array on top of our Cartesian mesh, right? So basically what we did here, we wrote the reader that reads CSV, CSV file, and then converts it into a three-dimensional Cartesian mesh. I see there are questions. What happens if you have 2 scalars? For example, 5-dimensional. Also, can I do scatter plots varying in time? Yes. So the answer is you can do both. So what happens if you have, well, if you have 2, so actually 3 questions. So what happens if you have 2 scalars? So if you have 2 scalars, you just need to define them. Oops, you need to define them right here. So you need to define 2 scalars, and it will be a, let's say you have 2 different variables, and then you will define 2 different variables here, or you can define a single variable with 2 components here, let's say a vector-dimensional vector field. Then you change this 1 to 2. So let's say if it's a 5-dimensional data set, then yes, you can do a 5-dimensional data set. So NumPy can supports for 5 dimensions, and VTK supports 5 dimensions as well. So you can define a 5-dimensional Cartesian mesh. It's just visualizing this mesh. You can only visualize it obviously in 3D. But yeah, both NumPy and VTK supports multiple dimensions. And the second part of the question is how we can define scatter points varying in time. So yes, you can do that. I'm not going to show you an example today, but you can actually find the examples. It's slightly more complex You can find examples in the VTK and ParaView tutorials, and I have links in the summary page. But what you need to do is you have to add some data describing time steps, some code describing time steps to the second request information script box. But the answer is yes, it's possible. I'm just going to not show it today in the demos, but it is in documentation. Any other questions? All right. So let's now, instead of writing a separate image file, a separate CSV file, let's actually try to define a function programmatically right inside our programmable source. So here we're going to simply set n to 100. So we're not reading any data. We're going to start from scratch. And then we define the Cartesian mesh. So the usual way, it's a 100 by 100 by 100 mesh, so 1,000,000 points in total. Then I define these 3 one-dimensional arrays, x, y, and z, that give me the discretization, so the points in x, y, and z. And then I compute data, which happens to be, in this case, it's a 3-dimensional array, which is described by this function. So it's called, mathematics is called a sine envelope function inside this unit cube. Well, actually not a unit cube, it's a cube that goes from 0 to 99 in each index. And then I take row. So row is a VTK, so single precision VTK array. Then I set its name density. So this name will appear inside ParaView. Number of components, 1 means it's a scalar field, not a vector field. Number of tuples is just number of points. So that's a 100 by 100 by 100 points. And then I simply go through all points. And then for each point, so there are 3 nested loops in Python, which is, as you know, probably know, is not very efficient. I simply set the point ijk. So the point ijk comes from the NumPy, 3-dimensional NumPy data array. And then I just set the point and I go through all points in 3D and I add each point to my VTK array. And then I add that array to my output, to my Cartesian mesh. All right. So the output type is the same VTK image data. And all I need to do is just paste this code into the script box. So just give me a second. Okay, that's VTK, volume image code. Here I have it. Let me open ParaView, and then I'm going to start from scratch. So I'm going to call the programmable source. And for the output type, I'm going to set VTK image data. And then I'm going to paste the code that I just mentioned right here. So here we're simply computing the function programmatically. We're not reading anything from the file. Compute the data NumPy array and then convert it to a basically take each point in data and assign a value to a point in the VTK array row, and then add that row to our output. And then I hit apply. And then it takes a while. And then it computes my output. So actually, yeah, it computes my output. And then if you remember from the previous example, I actually need to describe my output in the second box. So in the request information box right here. Now it's a 100 by 100 by 100 array. I hit apply. And here is my data set, right? So in this case, I'm going to switch to a surface view. And then I'm going to color by the value of my function density, right? So here we have the entire pipeline is just a single object where we define the function programmatically right inside the programmable filter. So as I mentioned before, doing things this way is not efficient. So because we are going through, there are a million points here, and it took a few seconds for me to actually run this. Because Python is not very efficient when you have these explicit loops. And really what you want to do is, instead of doing these loops by hand in Python, you want to take your 3-dimensional NumPy array and simply convert it to a VTK array, right? So the syntax is slightly different from the previous example, but here we have the same NumPy data array. We convert it to a VTK array. Number of components is 1, so it's a scalar field called density, and we simply appended, we set a scalar field on top of each point in our output, right? So let's just take that, and actually all I need to do is simply modify. So the request information box is going to stay the same, and I need to erase everything here in the script box, and then I will paste the code that I just showed into the script box right here. So output is the same, VTK image data. I hit apply, and here we go. It just recomputed it, right? It just recomputed it, and now it's actually much faster. So it took only a small fraction of a second. So this pipeline is more efficient than the previous example. All right, so now let's go to a more complex example. This is actually an example I copied from the ParaView documentation, and it appears in many different websites, but I think it's really neat because you're doing something more complex with polygonal data and you're setting up a cell. So the idea is to show this helix, right? So it's a single line that contains, in this case, 300 points. So here we're going to set the output type to VDK poly data. Polygonal data is simply, two-dimensional or one-dimensional, well, up to two-dimensional meshes, right? So surfaces, lines, et cetera, et cetera. So we set the number of points to 300. Length is each, so length is just the length along the x dimension. And 5 is the number of rounds in our helix. Then we have this variable index that is actually an NumPy array that goes from 0 to 299. We set the angle phi, so the angle phi goes, so here we have 2 times pi, rounds number of times, so 5 times, so we have five revolutions, and then we set x, y, and z for each point. So because index has 300 elements, x, y, and z will also have 300 elements. So these are the x, y, z coordinates of the points forming the helix. And the x coordinate is just a linear increase from 0 to 8. And then y and z are the sine and cosine functions, producing these circles. Then we have the coordinate NumPy array, which is simply a two-dimensional array. The first dimension is number of points, so 0 to 299, and then the second dimension is the component. So there are 3 components: x, y, and z. And then we set the point coordinates using this very simple syntax. Output.points is actually a variable that is already present in our output, and we simply set it to coordinates. And the output is once again, it's VDK polygonal data. So VDK polygonal data is the output where you define points, and then optionally, you can connect these points by lines forming cells. So to form a cell, we're actually forming a single cell in this example. To form cells, you set up these point IDs variable, just name of a variable, that is of type VDK ID list. And then you will have 300 points. You go through all 300 points, and then you set each point one by one. And what the syntax set ID means is you take the point I from our data array, and then you set it to point I inside our cell. So when we connect all points in a cell, they will be connected sequentially, starting from point number 0, going to point number 1, point number 2, and so on. And then you allocate a single cell, and then you insert this cell using the point IDs object, right? So basically, you add a single cell, forming a line where all cells will be connected sequentially. So let me run the first part of the script up to point where we set up, the points before we set up the cell. So it's the single helix code. Let me just show it here. So I'm going to go to ParaView. I'm going to start from scratch, reset, and then I'm going to call programmable source. So search for programmable source right here. And then output type VDK polygonal data. And then into the code, I'm going to paste everything up to, so including the points, but not including the cells, right? So, and then hit apply. And let's check what we get. So there are no errors. Information, you see that we have a type, output type is polygonal mesh. This is what our programmable source produced. We have 300 points. And on top of these points, we have an array called angle. And that angle is actually set right here. So yeah, we append an array called angle, which is simply filled by the phi values, so the angle values. And there are no cells here. So it says number of cells, it says 0, right? So we cannot visualize this as a cell. But what we can do here, we can actually switch to, so you see when I go to points, it doesn't show anything, surface doesn't show anything, because I have not defined a cell. So once you define a cell, then those output points and surface will show something. But here I can actually switch to a different view called PowerPoint Gaussian. And here it will place an image on top, a spherical image on top of each data point. And then I can actually color this by the value of my angle field. right? So here I have my helix, which is formed by cells, by points, but there's no line yet. So we have not defined the line yet. So to define the line, I need to paste the rest of the code. So right here, I'm pasting the rest of the code from the slide. So here we allocate a single cell, and this cell is filled by the points mentioned in the set, point IDs array. So when I say apply, nothing happened visually, but you can actually switch to a surface view, and now you see a line. And the line is, of course, very thin. It's just mathematically thin line, and you can apply a tube filter to the line to make it thicker. I just decrease the thickness, and here we go. So here we have our line, which is formed by 300 points and a single polygonal line cell. All right, so very neat example that is copied straight from the ParaView documentation. All right, so the next example is going to be slightly more complex. It builds on the previous single helix example. So now we have two helices. We have two helices offset by a phase shift, which is, which is set to pi divided by 1.5, right? So we define two helices. We have a points array, which we simply fill the points. We insert a point into the first helix. We insert a point into the single helix, and both helices have 300 points. So 300 points, the same length. It's just now we have two helices, right? That are offset by this phase shift right here. And then what we do, we add these points to both helices. So we add them to our output set points. If we run this code, then this will show us only points in the two helices, but not the cells. So next we need to form the cell that will show the first helix, the cell polygonal line showing the second helix. And then we also define these links. So what I'm doing here is, let's see. So here I'm filling both helixes. So number of points in the first helix is 300. Number of points in the second helix, second cell is 300. And then I set the IDs of the points. So here I form both cells, two helices. And then next, what I do is I define the links. So let's say every fifth point pair in the two helices is going to be connected by a link connecting these 2 points. So we're going to start from the third point. So that's Python counting starts from 0. So that's point number 2. And it turns out if you do the numbers, these will result in 60 links. So we need to allocate space for our two helices and for 60 links, right? So that's why we have 2 plus this is equal to 60, and this forms the 62 cells that we'll see in the visualization. So we form the first helix, we add the lines forming the 60 links, and then we just run this code. So let me switch to ParaView, and then I'm gonna, right here, actually let's start from scratch. I'm gonna apply, call the programmable source. And then it's VTK poly data, and into this, I'm gonna paste the code from the slide. So just give me a second. It's a longer piece of code. So here's the code from the slide. We hit apply, and we see 2 lines and 60 links. So in fact, when I go to information, it describes the output. So we have 300 plus 300, so 600 points in total, and we have 62 cells. So 2 lines plus 60 links, right? And then you can actually color these by, you can apply the tube filter and then make them thicker, these lines thicker. So let's say like this, apply, and then you can color them by, let's say, tube normal. So now we don't have any variables because I didn't have that in my code. And let's say by the X component of the tube normals, right? So you have 2 different colors depending on which side you're looking from. All right, any questions? Okay, if not, then let's go to the next example. So the next example is actually computationally more intensive. We're using a programmable source to output the same polygonal data set type, but this time we're going to produce a point cloud connecting 1 million points. So that's actually quite a large number of points. And what we're doing here is we are placing 1 million points around the origin, so 0, 0, 0, and the R radius is drawn from a normal Gaussian distribution, right? So a normal distribution centered at 0, and then going to stretching the interval from -infinity to +infinity. So that's why I have absolute, because the radius, I want a radius start from 0. So radius goes from 0 to +infinity, but of course it's a normal distribution that is peaked on, well, has a peak at 0. So there are a lot of points near 0, and then the number of points decrease exponentially as you go further away from the origin. And then theta is a one-dimensional array so this guy, random num points, is drawn from a uniform distribution 0 to 1. I'll multiply it by 2, subtract 1, apply arcsinus. So that makes sure that my theta is computed in such a way that my points cover the sphere uniformly in theta direction, so in the polar angle direction. And then phi is simply computed from a uniform distribution 0 to 1. So take the distribution and multiply by 2 pi, so it covers the entire longitude angle. Right? And then based on r, theta, and phi, these spherical coordinates, I compute the Cartesian components. I set up the coordinates array, so same array we saw before, containing 1,000,000 points and 3 components for each point. And then I use that coordinates array to set up the points in my output. And then I append a couple of fields, so the radius and the phi field. Right, so let me just take this and paste it into ParaView. So the code is point cloud. And I'm going to start from scratch. So apply the programmable source, and then VDK polygonal data. And I'm going to paste my code where I stop when I define these 2 arrays on top of each of all points, r and phi, right? So I'm going to say apply, and then I click on information. You see that there are no cells. We have not defined any cells, but we have defined 1,000,000 points, right? So to see the points, of course, if I switch to points, it doesn't show anything, because for that, I need to have at least a single cell. But I can switch to point Gaussian, and here I have my 1,000,000 points that I can color by my, let's say, phi angle. So here you see a phi angle that goes from 0 to 2 pi. And actually here you see the transition between 0 and 2 pi, right? So this is the 0th meridian, or I can color it by radius. Okay? Yeah, here we go. Or if I want to see the points in the surface or wireframe or point representation, then I have to create at least a single cell. And this is how I can do that. So here I create a cell, a single cell, which contains my points. So here all points are copied into this points ID variable. So I added all points to the cell, but the cell does not contain any lines. So instead of VDK polyline type, my points are, well, sorry, the cell is of the type VDK polyvertex. So it contains only the points, but not the lines. So let me show this. I'm going to take this code and I'm going to paste it at the end of my programmable source right here. Then I run it. And now in the information, you see that now I have 1,000,000 points and a single cell that I just defined. Okay? So that means that I can switch to, let's say, a points view. I can switch to a surface view, and that will give me my 1,000,000 points, right? Which is great. And there are some fun things I can do with this. For example, I can apply a cliff filter to this. Let's say like this. And it takes a while because I'm applying a cliff filter to data set with 1,000,000 points. So let's just wait. Polygonal data sets are not structured as opposed to Cartesian meshes, so they take longer to compute. So I'm hoping to show the distribution of the radius variable in a clip. So essentially something like this. All right, it looks like it's done. Yep, here it's done. And then here we're coloring by, let's say by phi, this is what it looks like, coloring by radius, that it looks like. Well, this is not very spectacular because the points are very small. So you can do two things here. You can either place a sphere on top of each point, but there will be computation quite intensive. I don't recommend that, but I can actually switch back to the point Gaussian view, and you can hide the plane. And I think this is quite nice because you see that there is a sphere on top of each point, and you can actually color it by different color map. Let's say switch to these color map, rainbow desaturated, that just has a lot of colors, so it'll appear more dramatically. And then you can actually modify, in the properties of the cliff filter, if you scroll down to representation, so you can modify the Gaussian gradients. You can make points thicker, smaller or larger. So let's set it to, let's say, this value. So each
and Alex, you have a question as well?
Larger. Yeah, I saw that. Yep, just a second. Yep. I can make the points larger, and I can actually switch to a different image, pre-computed image. So for example, this image, and as you can see, this is really, really instantaneous. So this is run on a GPU, actually integrated GPU on my laptop. And as you can see, it's really fast. And the result is quite spectacular, right? So 1 million points, and it's very interactive. So I get the results right away. And the question is, can the output be exported to use in, say, Unity or web interface? Not sure what you mean by web interface. So Unity, I'm sure it can be done, yes. So you can take the output and you can save the data set, and it provides you lots of different output types for your data set. So essentially you export it, let's say, as unstructured grid files or as polygonal data files or scene files. Yeah, there are lots of different output types. And then you can import it into Unity, yes. Web viewer, I'm not familiar with that. So sorry, I cannot answer. I don't know. But no, I'm sure the answer is yes, you can. So basically go to file and then save data as, or export scene as. So there are different, different things. So there are different scenes that are supported. And I'm sure some of these can be imported into Unity or web interface. So the answer is yes. But I don't have any experience with those tools, so I cannot show it. All right. So final example is, let's go back to, let's see, we have only a few minutes left, back to our original problem with the programmable, with the projection, right? So where we have a three-dimensional data set and we want to compute a projection. Well, here I have actually 3 codes that show how to do this. So this is less efficient way. We simply take the input. So now we do a programmable filter as opposed to a source. And we inquire about the total number of points. So there's going to be 1 million points. Side is a million to the power 1/3, so 100 by 100 by 100 points, 100 points on each side. So layer is number of points in a 2-dimensional layer, that's 10,000. Then we define a 1-dimensional flat array that contains the value of all million points, the value of density on all million points. And then we define the points, we define the projection array. We go through all points in our 2-dimensional layer, and for each point we set the values of x and y that are the same as the x and y in the original data set. And then the z is going to be offset by 20, so minus 20, offset relative to the original cube. And then 0 is the projection, right? The value of my column density along the projection. And then I go into the 3rd dimension, I simply sum it up. So I compute the column as the sum of all points of all densities in each column, right? So that results in a 2-dimensional array that I can simply set to the output. I add this column to each point, and then I take the points and I add them to the output. So the output of type PDK unstructured grid, and then I set the scalar, so the projection array as a scalar on top of these points, right? So when I run this will produce a projection. So let me show this. Just give me a second. These will show the projection. The problem is that because these are only points, again, I will not be able to visualize this as a surface, this projection as a surface. So let me start from scratch. I will import a data set because we need some data to actually compute the projection. And for the data set, I'll just take the sign envelope function that I saved as an SCDF file. So here we go. So here's my data. And then I just gonna apply the programmable filter to it. And then output type is gonna be VTK unstructured grid. And then I'm gonna paste the code that I saw in the slide right here, hit apply. And then nothing is shown, right? When I do surface, nothing is shown. And the reason is because I only have points, right? So I have these points. And then let me display the original data. So surface, show the density, and let's just switch to different color maps so we don't confuse the two. So let's switch to, let's say, this color map. All right, so here I have the original data set and then the projection. But the projection, as you can see, it now exists only at as points. So if you want this projection to form a surface that you can visualize as, well, as a surface, right? Right now we're looking at point Gaussian, but nothing shows up as a surface. You need to augment your code. You need to add this, right? So here we are basically going through all cells in our output surface. Well, all elements that we want to be cells. So we initialize a cell type quad that will contain 4 points. We allocate 100 by 100 cells, and then we just fill them with the points, right? So we go through this two-dimensional surface, and then for each cell we set the 4 points, and then we insert a cell. So it's of type VTK quad, so basically it's a quadrangle, and then we set the points. So if you add this code to our script, then you will see the cell. So now if I go to information, now I also have the not just the points but the cells. So there are 100 squared points and 99 squared cells. And now this thing shows as a surface or as a wireframe, you know, it just shows up. And once again, so I'm almost done. Once again, this is not terribly efficient because here we're still doing these explicit Python loops, and that is slow. So to speed up your code, what I can do is simply, instead of forming VTK, let's say polygonal data or VTK unstructured data, you can form a two-dimensional Cartesian array of type VTK image data, into which you take your three-dimensional array right here, and then you apply the NumPy built-in function. So I simply take my three-dimensional array, and then I use the sum function to compute a projection along the z-axis. And then I convert the projection into VTK array that I set to my two-dimensional Cartesian mesh. And then everything is much faster than in the previous implementation. All right, and the last thing that I want to show is this is actually something that just for fun, but just to show you that you can use programmable sources and filters for not just for scientific data, but for toy examples as well, toy animations as well. So as you know, every year we have this visualization competition, and in 2017, one of the entries was from Jarno van den Kalk from the University of Ottawa, who was a postdoc there at the time, and he produced this beautiful scientific visualization. And the first part of his animation was this toy visualization of wind turbines in a landscape with the grass, the sky, the house, et cetera. And all these elements we produce as either regular sources or programmable sources. So to show this, what I'm going to do is I'm going to start from scratch, and I'll just open a state file, ParaView state file that contains that entire visualization. So load state. I'll just need to navigate to this guy, and here it loads. And here's my visualization, right? So you see this very nice house that is actually constructed as, there are walls, roof, doors, and windows. So the door is simply a plane, right? Window is simply plain because these are planes that I saw before when we were dealing with a 100 squared mesh. Into which I assign the textures. I apply the textures to this plane, so that is really easy to do. And the grass is a programmable source, and the reason for this is because grass is it has these small hills, so it's slightly random, so that it doesn't look like just a single surface. And I can show this as a wireframe. So you see, if I call it by, if I remove the texture, you will see what the underlying mesh looks like. Let's see, where's my texture? Yeah, it's somewhere there, but I don't see it right now. Yeah, I don't see it right now, but it's somewhere there. So the idea here is what I want to show is that it's a slightly random surface to which he applied the texture, and it looks nice when actually viewed as a surface. And then the same for the walls and the roof. So the roof is slightly more complex because it's actually two planes, and for that you can use two plane sources, or you can use a single programmable filter. So there is the roof, and then there are the walls that are slightly more complex because you have these, this triangular shape and so on. So anyway, that's all I wanted to show you today. And I'll just show you the very last slide, which contains the links and some notes about the workflows in Programmable Source and Filter. So I find that it's really useful to use a print command because it can tell you, provide more information on the type of variables and, what kind of attributes and functions you have inside the namespace of these variables in VTK. And you use the print command right from inside the programmable source or filter. So when you allocate variables and if you try to fill them before allocating them, then ParaView will crash. And that's unfortunate, but there's no way around it. So when you try to fill in structures that don't exist, ParaView will always crash. So be aware of that. And one way around this is you can, pay attention, of course, to what you're doing, but you can, when you have a partially constructed workflow pipeline, you can simply save it as a state file. And then if ParaView crashes, you can just, recover from the last saved state file. So everything I showed you today is mentioned in the ParaView wiki documentation. There's a nice talk by Jean Favre from the Swiss National Supercomputing Center about converting the programmable filter into a standalone plugin in ParaView. And the first half of his talk is actually, he talks entirely, not about the plugins, but just about the programmable source and programmable filter. So really good presentation. And then a future topic is, of course, how to convert everything I showed you today into a plugin that you can load into ParaView. And then you can use this plugin as a regular filter or a regular source with its own GUI controls. And that's a topic for another presentation.